Hi guys, welcome back to Gore Math Circle's Mathcounts training. Now, this is session 6 of a 12-part series. If you haven't watched the other videos, go ahead and watch those. And my name is Mugil Shanmugam. I'll be presenting all these videos for you guys. Okay, so let's get right into it. So what exactly are we going to be learning today? So we're going to be covering the following broad topics. Number 1 is digits arrangement. So often you'll be asked to find like the greatest product that you could form with these numbers, or the smallest product that you can form with these numbers. So that's what we're going to be covering in digit arrangements. The next one is we're going to be going over some geometry formulas. Obviously, we won't have time to go over each and every single small formula, but we'll be going over the broad topics that will help you in the overall concepts of math counts. We'll be also going over modular arithmetic, and finally, divisor and divisibility. And under these, we have subtopics, so basic knowledge and sound problems for digit arrangements. For geometry formulas, we have examples and theorems, as well as sample problems. For modular arithmetic, we have definitions and theorems, as well as sample problems. And for divisor and divisibility, we have the definition, number and operations based on divisors, and the sample problem. Okay, so let's go over first digit arrangements. So we're given a set of digits, and we're often asked to find like the smallest possible product or the largest possible product. So generally it'll be like, you have 4 digits, 1, 2, 3, 4. Find the biggest product you can make with these numbers, or something like that. So here's a quick rule of thumb we'll need throughout this, and this will help you remember the rule, and you can apply it to any digit numbers. So the smaller digit will go with the larger number if you want to get the greatest product. So we'll see what I mean by that in a second, but for now, just know that you're always going to match the smaller digit that you have with the larger number. So our first rule is going to be if A is greater than B and C is greater than D, then AD times BC is going to be greater than AC times BD. So these two parts of our inequality are something you want to be like really familiar with this, because we're going to be using this to find the smallest and largest product. And basically this line over the top, so in decimals, generally this means like a repeating number. But here, what this basically means is we're not going to be multiplying A and D, we're simply just going to put them together. So for example, let's just say A is 1 and D is 4. So I'm not going to be multiplying them to get 4. I'm just going to be putting them next together to get 1 and 4, which is 14. So that's what they mean by putting this little line over our AD and our BC here. Anyway, so AD times BC is going to be greater than AC times BD. So the greatest product that we can get is going to be DA times CB. So this is the greatest product that we can get. The greatest possible product is going to be DA times CB. Now, what does D, A, C, and B generally represent? So what these generally are going to represent is A is going to be like the smallest number you have, D is going to be the biggest, and C is going to be the, I would say, second biggest, and B would be the second smallest. So similarly, the smallest product that we can form with these numbers is going to be AC times BD. That should be pretty self-explanatory. All you need to do is put those two digits together based on whether like they're the smallest or they're the biggest. Based on that, you can put them together and then you can multiply. Okay, so those are just the basic formulas that we need to know. So let's go on to the next slide. Okay, so if we're given the digits 1, 2, 3, and 4 to use in the formation of two-digit numbers, right? So this is a general problem you're going to get. They're just going to like give you a bunch of digits, and they're going to say form this many digit numbers, and what is the smallest possible product, or maybe they would ask the biggest product that can be formed. So first we need to learn what formula to use, and here we're looking for the smallest possible product, and that was AC times BD. So that's the formula we're going to use. So AC times BD. Now here, what is my smallest number, or my smallest digit? 1, right? So 1 is going to be my A value. Similarly, my C value is going to be 3. So that's how I get 13 over here. And note how I'm not multiplying 1 and 3. I'm just keeping them as 13. Similarly, B is going to be 2, and D is going to be 4. So I get 24 over here. And then when I multiply them together, I get 312. So this is the smallest possible product that can be formed. So this is pretty simple as long as you remember how to put the digits together and how to identify which digit goes with A, B, C, D, so on. Okay, so here's a sample problem, right? Create two 3-digit numbers. Okay, so this is not exactly the same as this one because now we have 3-digit numbers using the digits 4, 5, 6, 7, 8, 9. You have 6 digits here, and you want to find the greatest possible product. and you can only use each digit once. So you want to make two 3-digit numbers, right? Two 3-digit numbers that when multiplied are going to give you the greatest possible product. So how exactly are you going to do that? So for this, the hint I'm going to give you is you're going to have to use this rule of thumb. Smaller digit with larger number will give you the greatest product. Smaller digit with larger number. So based on the formula you have here, try to apply this based on what you know and try to expand the pattern that we already have. Okay, so pause the video here, go ahead and try this problem. Okay, so hopefully you tried out the problem, so let's go into the answer. Okay, so the first step is to use our two largest digits to start making the numbers. Remember? So here you can see we're going to use D and C as the first digits. So it makes sense that we're going to use the biggest digits here, 9 and 8. As you can see, I'm putting like blanks here just so I know that I still need to add some numbers in. Now we can use our rule of thumb to pair up the next digits, 6 and 7. So if I just consider this 9 blank blank and 8 blank blank, obviously this 9 blank blank is a larger number. So the smaller digit, that's 6 right here, is going to go with the 9. And the bigger digit is going to go with the 8. So that's how I got 9 6 blank and 8 7 blank. Now again, 960 and something is definitely going to be bigger than 870 and something. So that's how I know that the 4 is going to be going with this, and my 5 is going to be going with the 8 7. So based on that, I get my two numbers, 964 and 875. So now we got our two numbers, our two 3-digit numbers. Now we can just multiply them, and that's how we get our greatest possible product, which is 843,500. So once again, that was pretty simple. The main thing you need to realize was that you need to use this rule and kind of expand the pattern that we already have. Okay, so again, your answer here was 843,500. Okay, so let's move on to the geometry formulas. Okay, so again, as I said, I'm going to be going over mainly the main formulas. Here's the book that I got these formulas from. So if you want to go out and check that out, or if you want to look at the formulas, go ahead and do that. I'm just touching upon the main formulas here. So these are just going to give you like a basic idea of the formulas you didn't know. Make sure to go check out the more in-depth formulas for different specific cases. Okay, so if I have like corresponding rectangles in a bigger rectangle, right, and one of them has an area A, one of them has an area B, one of them has an area C, one of them has an area D, then A times B is equal to C times D. And remember, if they're corresponding, they're in proportion and everything. Similarly, A plus B is going to be equal to C plus D. So again, we have the area of these smaller rectangles, and if they're corresponding, we can make these following relationships. And then for corresponding segments, so the same thing, but now we have line segments that like go across like this or like this. Then it's going to be A squared plus B squared is equal to C squared plus D squared. And again, A here is going to be like the length of one of those segments. Now, if I have A, B, C, D as a trapezoid, and AB, BC, CD, and DA are tangent to this circle. So what does tangent mean again? Tangent means that the line is only going to touch the circle at one point. So I have a trapezoid and I have a circle inside it, and all the sides are tangent to the circle. Then AD plus BC, so my two sides, are going to be equal to the other two sides, AB plus DC. Okay, so again, this is if the circle is going to be inscribed in this. So once again, these are just some quick formulas that you can use when you have corresponding rectangles and so on. And now let's move on to some more trapezoid formulas. So in the same trapezoid, so we still have a trapezoid, we still have a circle inside it, but with AB parallel to DC. So here, AB was our top and DC was our bottom. But now AB and DC are parallel, and we have this OE segment that's perpendicular to CB, and OD is equal to OA. Then the area of ABCD is going to be equal to CB times OE. So we have a line segment in this trapezoid now, and it has a point O on it. Then we can find our area, which is CB times OE. So again, this might be a little helpful to, like, if you want to understand it a little better, you may want to search up an image of this, so it'll be a little easier to understand with the trapezoid. So once again, in the same trapezoid, so again, we have a trapezoid, we have a circle in it, but with the diagonals DB and AC. So we have two diagonals that cross each other, and they're crossing at this point O, which is there's a line, and the midpoint is O, where these two diagonals cross. Then we have the following equation: 1 over AB plus 1 over DC is equal to 2 over EF. So again, pretty simple equations, but basically when we have these lines, diagonals, segments, like in this trapezoid, this is how we can solve it. Okay, so now let's move on to a few triangle formulas. Okay, so many people know the basic triangle height formula, 1/2 BH, or AH in this case, because A is my base, presumably. So if we have A, B, and C, and we have the height H on the side A, so side A here would be your base. We're just going to call it side A. The area of the triangle is 1/2 AH. You could also write this as 1/2 BH, however you want to write it. Now, there are some other formulas you can use to find our area. The first one is 1/2 AB sine C. And you could also change this to like 1/2 CB sine A, or so on. So what this basically means is if you have a triangle, you know the lengths of two sides, and you know the sine of the included angle, then you can find your area. And here's Heron's formula. So in this formula, you're going to find the semi-perimeter first. So semi-perimeter is going to be all the sides added up over 2. And then I'm going to find the square root of the semi-perimeter into semi-perimeter minus A, into semi-perimeter by minus B, minus S minus C. So again, what we're going to do is we're going to find our semi-perimeter, and then we're going to multiply it by S minus A, S minus B, S minus C. And then finally, we're going to take the square root of everything. Don't forget the square root. And finally, if we have a circle in a triangle, right? So if we have a triangle and then a circle is inscribed in it, and we have a radius that's a right angle with the base, then our radius's length is going to be area over semi-perimeter. And we can always rewrite this as 2 times the area over our perimeter, whichever one's more convenient for you. Because like sometimes you may have the semi-perimeter, you may not have the area, so based on whichever one is easier in this situation. But again, these are just some basic triangle formulas that you can use. So the majority of them are used for area, and this one I'm just teaching you how to find a radius if you have an inscribed circle and you're trying to find this radius that is at like a right angle with the base of the triangle. Okay, so let's move on to our next slide. Equilateral and right triangle formulas. Okay, so let's just say that we have a circle with an inscribed triangle, right? So we have a circle and there's a triangle inside it. And we want to find this radius capital R. So capital R is actually going to be equal to 1/3 A2 times the root 3. Now, this is only going to work if you have an equilateral triangle inscribed in your circle. So make sure it's an equilateral triangle, and then we can find our radius by doing 1/3 times A times root 3. Similarly, if we want to find the height of an equilateral triangle, well, this one is simply going to be little r. So I've used big R for the first situation that we have. For this one, when we're just finding like the general height of an equilateral triangle, we're going to be using this one. And finally, this is another formula we can use. But again, this is little r and this is big R. So these are two different scenarios. Make sure to like make that distinction in your head. Maybe you want to write it down. However, you want to just keep track that big R and little r are not the same. So if I have an equilateral triangle, this is the formula I'm going to use, right? So if I have an equilateral triangle and I want to find this altitude in the middle or a height, then what I can find is 1/2 times A times root 3. And again, here A is going to be one of the lengths of the sides. And in an equilateral triangle, all these sides are going to be equal. So you just need to know one of them. And similarly, now in this situation, we're going to be going back to this one. If we have a circle in a triangle, so before we had a triangle in a circle, but now we have a circle in a triangle and we have a radius that is at a right angle with the base of the triangle, then the height of this triangle is going to be 1/6 times A times root 3. Now, you may be noticing a pattern of the root 3 and then the 1/2, 1/3, or 1/6. So that's going to be derived using 30, 60, 90 triangles, or in this case, it's just going to be 60, 60, 60 triangles. So if you can draw out one of these triangles in your circle or in your rectangle, wherever you find it, then it's going to be easy to derive these formulas based on, even if they give you like a new situation that we haven't really covered. So make sure to know how to use a 30, 60, 90 triangle. That should have been covered before, so just make sure to know how to do that. And you probably already know a 45, 45, 90 triangle. Those two will help you when solving these problems. Okay, so angle bisector theorem. So if we have the triangle ABC, which is a right triangle, right, then our radius is going to be AC plus BC minus AB over 2. So again, we're going back to this original situation we had with like a circle in a triangle. So in that case, and we have a right triangle this time, so the right triangle, there's a circle in the right triangle, then AC, which is one of the sides, plus BC minus AB over 2 is going to give you R. Again, so this is going to be based upon whether you have a right triangle. Now here we have the angle bisector theorem. And what this states is if I have this triangle like this and I have this line running through the middle, this is called a bisector. Why? Because it divides this angle into two equal parts. So if I have my side here A and my side here B, and this is a bisector, then A over B is going to be equal to C over D. So again, you have to have a bisector in the triangle, and then it makes this proportion of A over B is equal to C over D. Okay, so then again, that's just a quick formula that you can use when you're trying to find proportions. Now we have a few more triangle relationships. These are pretty simple, so you shouldn't have too much trouble with this. This is pretty self-explanatory. So if I have two triangles with the same area, then they have to have this equal bases and equal heights. So then if two triangles have the same height, then the ratio of the areas is going to be the ratio of the bases. So if they both have the exact same height, then their bases are different, and that's also going to determine how their areas are different. Similarly, if they have the same base, then the ratio of the areas is the ratio of the heights. So based on that, you can probably figure out a ratio of the areas, or the heights in this case, and based on that, you should be able to solve triangles if they give you a certain value and ask you for other values. Now, there are many similar triangle area relationships. I encourage you to go explore them, search up triangle area relationships, or maybe a triangle with shaded regions to find different areas, and based on that, you can find many more relationships that can help you when you're studying this in general. Okay, so now we're going to go over circles, sectors, and volumes. So in a sector of a circle, so a sector of a circle is basically like a region of a circle, right? I would say a piece of a pie. And you have L is the length of your arc. So if you have an arc like this, right? So the pie crust, you could say. And A is the area of the sector. So how big your pie slice is, that's going to be A. Then your length is going to be 2 pi r times theta over 360. Now theta is the angle of your pie slice. So however wide my pie slice is, if it's like this or if it's like this, based on that, the angle of that, the interior angle or the central angle you could call it, is going to be theta. So 2 pi r times theta over 360 is equal to L, and your area is going to be pi r squared times theta over 360. So again, here, 2 pi r is the circumference of the whole circle, and pi r squared is the circumference of the whole circle. And then we're going to multiply that by our interior angle here, just so we can get only the area and length of the sector of the circle. Now here we have some cone and sphere formulas. So if the total surface area of a cone is going to be the area of the cone plus the area of the base. So make sure to add both of them when they ask for the total surface area of a cone, because the base is also part of the area. So here we're going to have pi times r, so pi times radius times s. So the s is going to be your slant height. So that's going to be the height of the cone on the slant. And that's going to be added with pi r squared, which is simply the area of a circle, the base. Your surface area is going to be 4 pi r squared, right? This is for a sphere. I'm sorry I didn't mention that, but this is for a sphere. 4 pi r squared is how you're going to find the surface area. For the volume of a cone, it's going to be 1/3 pi r squared times the height. So slant height is going to be slanted, and normal height is just going to be straight up. So that's how you can differentiate between the two. The volume of a sphere is going to be 4/3 times pi r cubed, right? And you could also rewrite this as 1/6 times pi d cubed. And here d is your diameter. Okay, so then again, these are just some quick and easy formulas that you can use when you're trying to form like a circle or a huge circle part of a 3D figure. Okay, so let's move on to our sample problem. Find the sum of the circumferences of the 3 small circles. So here we have one of the small circles, here we have one of the small circles, and here we have the final circle, given that the big exterior circle has a diameter of 10 centimeters. So this line right here is 10 centimeters total. So based on that, they're asking you to find the sum of the circumferences of the 3 smaller circles. Okay, so you may be wondering, well, this isn't directly related to one of the formulas we learned. However, this is how you're going to see problems on the Mathcounts exam. They're not going to be directly related to the formula you learned. You're going to have to apply one of the formulas. So here we went over the circumference formula and a few of the extensions of this formula. So see if you can apply that to this circle. Okay, so go ahead and try to solve this one. Okay, so hopefully you solved that out. Let's see how we can get the answer for this one. Okay, so we can solve this based on our existing knowledge of formulas, right? So C1 plus C2 plus C3, so our 3 circumferences, when we add them up, that's going to be the same as 2 pi r1, so this is our first radius, 2 pi into our second radius, plus 2 pi into our third radius. And we can rewrite this as pi into 2 times our first radius, plus 2 times our second radius, plus 2 times our third radius, which is equal to pi times diameter, right? Because this is my first radius, this small segment that I'm kind of highlighting right now. So 2 times the radius is going to be the whole diameter of this circle. If you do the same thing for the rest of the circles, you're going to add them all up to get the big diameter here that we already know is 10. So then that's simply just going to be 10 pi. So our answer here is 10 pi. So this one, many people would have overthought it and tried to do calculations, but here you really just needed to like kind of reorganize your equation so you already had everything you needed. Okay, so again, your answer for that one was 10 pi, but let's move on to our next topic. So modular arithmetic. The integers a and b are congruent modulo m if a minus b is divisible by m. So here, m is going to be a positive integer greater than 1, and it's called your modulus. So what exactly does this equation mean? Here, this means congruent, 3 lines. But what this means is a mod m is going to be equal to b mod m. So what exactly does that mean? Again, so let's just say my a is 23, and my m is going to be 5. 23 mod 5. What that's basically asking me is, what is the remainder when I do 23 divided by 5? The remainder is going to be 3, right? There's 3 remaining. So 23 is going to be congruent to 3 mod 5, because when I do 5 divided by 3, my remainder is 3. Exactly. So based on that, that's how we get our congruent modulo, right? 23 and 3 mod 5 are going to be congruent because they both have the same remainder when divided. And that's what mod basically means in the simplest terms. So yeah, again, this is a fancy way of saying that the same remainder is obtained when a or b is divided by m. Okay, so just take a moment to just quickly go over what a modulo is, and let's move on. Okay, so here's an example of a modulo system. If a modulo 7 system applies in the 7-day week system. So here we're going to take the example if today's Thursday. Well, today's actually Sunday, but let's just go with Thursday. What day will it be 30 days from today? Okay, so 30 is going to be congruent to some b mod 7. So when I divide 30 by 7, my remainder is going to be 2. So that means 30 is congruent to 2 mod 7. So here they've worked it out, or I put in the work here where you're subtracting your multiple 7s, but you really didn't need to do this. All you need to do was divide 30 by 7, find your remainder, and that's going to be your b, because 30 is congruent to 2 mod 7. So now that we know that it's 2 mod 7, we just need to add 2 days to our Thursday, and we know that the day is going to be Saturday, 30 days from now. So again, basically all this is saying is a and my b over here both have the same remainder when divided by 7, mod 7. Okay, so here we have a quick review of division in a form of a theorem. So if I have a divided by b, that's going to give me q plus r over b, right? So my remainder over my b, and my q is going to be my quotient. So again, a divided by b is my quotient, and we can also rewrite this as a is equal to quotient times whatever I'm dividing by. Now, Here we have our first modulus, actual modulus theorem. So A is congruent to B mod the LCM of these multiple values of M, right? So if I have this different forms, let's just say this is 1, 2, 3, 4, 5, so on. Now I can make this kind of shorter, and I can rewrite it as A is congruent to B mod the LCM of MI, or just MI in general. So what this means is if the LCM of all of this, it helps in this, the LCM of just one of these numbers or two of these numbers will work here. So this is basically, I have this big LCM of multiple numbers and they all work in this modulus to make a congruent modulo. Then I can use it, I can use the same thing, but I can only use one of these. So I can use only M1, only M2, and I can still get congruent modulo. Okay, so the reverse of the previous theorem holds true too. So what I mean is, let's just say I have A is congruent to B mod M, and A is congruent to B mod N. And let's say that these two are not prime. So ignore the writing above, just focus on these two. Then I can also rewrite this as A is congruent to B mod LCM of M and N. So I can combine M and M if I know that both of these hold true. So that's why I'm saying it's kind of like a reverse, because here I have the LCM and I'm breaking it down into just one. Here I have my just ones and I'm trying to make it together to form the LCM. Now, when A and B are prime, it's basically the same as the LCM, except we're just going to multiply them because they're prime. You can just multiply them to find your LCM. So here it's just M times N. Now, if M is divisible by N, then we can create this. A is congruent to B mod M, then A is congruent to B mod N. So if M is divisible by N, then it holds true for both M and N as what I'm going to be dividing by to find my remainder. So again, these are just some quick and easy formulas that you can use when you have something big, you're trying to make it smaller, or when you have something small, you're trying to expand it. Okay, so here are some more theorems. Similarly, we can raise both A and B to the same power and keep the same relationships. So let's just say that I have A to the power 1, B to the power 1, mod M. I can also do A to the power 2, B to the power 2, mod M to the power 2. Yeah. So like that, we can just all raise them to the same power. Now when we want to do operations, then what we can do is A is congruent to B mod M, and we can do C is congruent to D mod M. So these are our two basic things that we're going to be using in our equation. Then we can also do A plus C is equal to B plus D mod M, and A times C is equal to B times D mod M. And we can also do A minus C, B minus D. Now there isn't any real division, I would say, using modulus and congruent modulo, but we do have cancellation rules. So if I have AC is equal to BC mod M, or congruent to BC mod M, then if the GCD of the factors are 1, then we can simply just cross out the factors. But if the GCD is greater than 1, we can remove the common factors, but the mod M will become mod M over D. So if we have the common factors on both sides, based on what the greatest common divisor is, then we can make a decision on whether we can just cross them out, or do we have to divide our mod M by D2. Okay, so, sorry, I meant divide, well, we have to change it to mod M over D, or M divided by D. Okay, so here's our last set of theorems. If A, B, and M are all divisible by D, then A times X, okay, so for now, let's just consider this. A times this unknown value X, this variable X, is congruent to B mod M. So then I can change this to A over dx is congruent to B over D mod M over D. So what does this mean? This means that either way, the value of X here is going to be the same. There's going to be no changes in its value. So in theory, both these equations would hold true, and they're both equivalent. Now here, we're expanding it here. So if I have this A1 value, B1 value, and this holds true, and I have A2, B2, and I keep going till I get AK, BK, then we also know that A1 times A2 until AK is going to be congruent to B1 times B2 times until BK mod M. So basically, again here, we're just expanding it to get our mod M. And we can basically just multiply both sides. But again, these are just some quick theorems. So from the start, we have these theorems, which are basically about condensing or expanding. And then we have this one's about kind of like adding, subtracting, multiplying, and cancellation. And finally, here we have them about like an equation, or if we want to kind of multiply when we have multiple values or multiple equations that hold true. Okay, so here's the sample problem. If a certain number is divided by 2, 3, 4, or 5, and the remainder is 1 in each case, what is the least number that satisfies this condition? Okay, so here basically you're kind of given multiple modulo, and they're trying to ask you what is the least number that satisfies these conditions. So here, think about it this way. You have this many modulo, you want to condense them into one. So try to figure it out using that hint. Go ahead and solve this one. Okay, so hopefully you paused the video, you solved it. Let's go into the answer. So theorem 3 states that if a and b are constant for values of m and n given, we can find the LCM of these values and create an equation of congruent modulo. So if I have a is congruent to 1 mod 2, which we already know, and they also gave us this, and this should be 5. So a is congruent to 1 mod 5. So then we can combine all of them using this theorem, right? Which said that we can just multiply them if they're prime. They're not all prime. We need to find the LCM of all of them, right? Because they're not all prime. So that was what theorem 3 said. So when we find the LCM of all of them, we get 1 mod 60. So this means I have a remainder of 1 when I divide by 60. So 60 plus 1 is equal to 61. So 61 will have a remainder of 1. So it satisfies this condition, and it's the least value that satisfies all these conditions. So based on that, that's how I got my answer of 61. Okay, now let's move on to divisor and divisibility. So a divisor is a number that divides another number without a remainder, right? That should be pretty simple. We all learned this when we were in elementary school, right? A divisor is a number that divides a dividend. Now, if we prime factorize an integer n as such, here's my first prime factor to the power a, so like 2 to the power 3, and 3 to the power 4, I guess 7 to the power 3, and so on. This is my prime factorization of this, right? My first prime factor to a certain power, my second to a certain power, my third to a certain power, and so on. So the number of divisors of this number n is going to be a plus 1, so the power, the first prime factor plus 1, into b plus 1, into c plus 1, until n plus 1. And we do this for all the prime factors. So how many of prime factors I have, I'm going to have this many things that I have to multiply by in my equation. So a plus 1, b plus 1, c plus 1, till n plus 1 here in this situation, because I only have a, b, c, and n. Now the sum of the divisors is going to be my first prime factor to the power a plus 1 minus 1 over prime factor minus 1 into prime factor 2 b plus 1 to the power b plus 1 minus 1 over the prime factor 2 minus 1, and so on. So you can see the pattern here. We're basically going to find it from over here, and we have to add 1 to our power, then subtract it from 1. And we do the same thing in the denominator, except here we're not going to take it to any power. We're simply just going to subtract the 1 from the prime factor. And this is how we find the sum of all the divisors. So again, this formula seems scary. It's really not. As long as you remember the first term, you know all the other terms. So it's pretty easy. Okay, so here we have the product of divisors. So my product is going to be the first prime factor to the power a, second prime factor to the power b, and so on. And then this is all going to be, so once I multiplied all of this inside the brackets, then that's going to be to the power, or inside the parentheses, that's going to be to the power a plus 1 into b plus 1 into c plus 1 all the way up to m plus 1 over 2. So again, here we have all the prime factors to their respective powers, and then here you may see that this is the same as the number of divisors, so the number of divisors over 2. Finally, consider the following number where we have j, a, b, c, and m, and they're all non-negative integers. So I have 2 to the power j, and then I have a bunch of prime numbers. And p1, so p1 is my first prime factor, pk is my second prime factor, and so on, right? And they're all prime numbers other than 2. So these are all other prime factors, and this is how I'm factorizing my n. So before we factorize n as like this, now I'm just including a 2 to the power j, and then I'm having other prime factors over here. So what I'm going to get is I want to find the number of divisors of each parity. So how many odd divisors, how many even divisors. So if j is equal to 0, then there are no even divisors. So this would mean that it's 2 to the power 0, which is 1. So there are no factors of 2 in this, or 2 does not divide this, basically what that means. Then there are no even divisors. If j is equal to 1, so it's 2 to the power 1, the number of even divisors is the same as the number of divisors for any n prime factorized in the way we discussed before. So what this means is if I use this formula on my 2j and then so on, then that's going to be how many even divisors I have if j is equal to 1. If j is greater than 1, then the number of even divisors is j into a plus 1, into b plus 1, into c plus 1, all the way until n plus 1. And the number of odd divisors is going to be the same thing, just don't multiply the j at the beginning. So again, if you know this first formula about number of divisors, and you need to know the sum formula obviously, and the product one, then you can pretty much find out your other n factorization and the number of even and odd divisors. But then again, these are just some formulas that you need to know, but if you spot the patterns in these, it's pretty easy to understand. Okay, so here are the factors of counting numbers 1 to 100. So what I basically mean by this is like the number of 1, it only has one factor. All prime numbers only have 2 factors. So like this, sometimes it's helpful to create a table of like, oh, how many factors does 12 have? How many does 16 have? And so on, just in case you're asked a question around that basic topic. So here's a small table. It's super small, but that was just a basic of one of these tables that you can find online. So I'd encourage you to go check out one of those tables just in case. And by check out, I basically just mean kind of review it and see, well, if I want numbers with 4 factors, how many numbers are like that in counting numbers 1 to 100 and so on. Okay, so here we have some divisibility rules. I know that many of you have probably already learned these, but I'm quickly just going to go over them because they're often really helpful when it comes to figuring out these problems. So the last digit is even, then it's divisible by 2. If the sum of the digits is divisible by 3, then it's divisible by 3. If the last 2 digits form a number divisible by 4, it's divisible by 4. If the last digit is 0 or 5, then it's divisible by 5. If the number is divisible by 2 or 3, it's divisible by 6. If the last digit doubled and subtracted from the number is divisible by 7, then it's divisible by 7. So what I mean here is like if you take the last digit, you multiply by 2, and then you subtract it from the number itself, and you get your difference. If that's divisible by 7, then the whole number is going to be divisible by 7. If the last 3 digits are a number that's divisible by 8, then it's divisible by 8. And these are just the first 8, and then I'll move on to the next ones. If the sum of the digits is divisible by 9, it's divisible by 9. If the number ends in a 0, it's divisible by 10. And if you add every other digit, then add the remaining digits. So if I add my first and my third digit, and then I add my second and my fourth digit, and then if I subtract the 2 sums, and if a result of 0 or a multiple of 11 results, then it's divisible by 11, the whole number. If a number is divisible by about 3 and 4, it's divisible by 12. If you delete the last digit, so if I take out the last digit, and I subtract 9 times that digit, and the difference is divisible by 13, then the whole number is divisible by 13. If the last 4 digits form a number divisible by 16, then it's divisible by 16. And for the rest, so obviously you don't want to remember each and every one of these divisibility rules. You kind of want a shortcut for some of them, right? So for that, what you need to do is you want to split them up into prime numbers that are relatively prime to each other and check the divisibility by each one. So if I have 18, I can split it up into numbers that are relatively prime, which is 2 and 9. So what do I mean by relatively prime or coprime? That means that 2 and 9, if you consider them, they only have one common factor. 1. They don't have any other common factors. So you want to find 2 prime numbers like that make up the number you want. So if I'm looking for the divisibility by 18, let's just say, then if I use 2 and 9, right, I know that both those are relatively prime, and then I can check whether the number is divisible by 2, if it's divisible by 9, and then if I know that it's divisible by both those, then I know that the number is going to be divisible by 18. So based on that, if you find these 2 relatively prime numbers and break it up like that, you can find the divisibility of all these numbers. Okay, so as long as you kind of remember the last one, you should be fine. Most of them, you probably already know them, or even if not, you can use the last rule to figure out the rest of them anyway. Okay, so here's a simple problem. How many positive integral factors does n have if n is equal to 6 squared times 15? So how many positive integer factors are there if n is equal to 6 squared times 15? here's your hint. This is not a prime factorization, so make it into a prime factorization first before you try to find how many positive factors exist for n. So go ahead, pause the video, and try to solve that. Okay, so hopefully you solved the problem. So let's see how we can get the answer for this one. Okay, so if I break n down into 2 times 3 to the power 2, because again here it's 6 squared, that's not a prime number, so that's why I'm breaking it down into 2 times 3 to the power 2. And here 15 can be broken down to the prime factors 3 and 5, then I can rewrite n as this prime factorization. 2 squared times 3 cubed times 5. Now, what is our formula for the number of factors? Well, if we go back here, you could use either one, but here I'm just going to be using this one. Our factor, or like our formula, is going to be a plus 1 into b plus 1 into c plus 1 until n plus 1. So basically, all the powers of the prime factors plus 1. So if I go back to my problem that I had, I find that the first one is 2, the first power is 2, the second power is 3, and 5 has a power of 1. So 2 plus 1 into 3 plus 1 into 1 plus 1 is going to be 3 times 4 times 2, which is 24. This means there are 24 positive factors of n. So pretty simple, as long as you just remember that formula and you just solve based on that. So again, here we just found the powers, so make sure to break it down into the prime factorization. Here they purposely gave you it as 6 squared times 15 because that makes you think, oh, I already have it in prime factorization. But make sure to check that it's actually all prime factors, because if you did it using just 6 and 15, you would not get the right answer. So once I've broken it down and then I use the formula, I can find there's 24 positive factors of n. Okay. So thanks for watching, guys. Please like and subscribe if you enjoyed the video. Leave a comment or email us with any questions. And thank you for watching. I really hope you enjoyed it. And make sure to tune in next week for the next video. Bye, guys.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatcircle.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email, but without the info and the end. So bye!